In our previous work on solving polynomial equations, we've had polynomials where the solutions were fractions. Yet, we didn't have any fractions in our factors. How does that fit with what we've just been saying about roots and factors? Let's consider this example. We're told that the number 2/3 is a root of this polynomial. We can check that by plugging 2/3 in to that polynomial on our calculator. I'll take 2/3 and just store that in my variable, and then I'll punch in my polynomial, 6x to the third plus 23x squared minus 12. I really do get 0. When x is 2/3, that polynomial really does evaluate to 0. That tells us, well, x minus 2/3 should be a factor. To find the other factor that goes with that, we can use the synthetic division that's set up here. Notice here we have the coefficients from our polynomial. We've got a 6x to the third, 23x squared. There's no x term, so we've got 0x, and then negative 12 for our constant. The actual synthetic division process is going to involve a bunch of fraction arithmetic, so I'm going to grab the calculator back to actually use for that synthetic division. I start by just copying the 6 down, and then we multiply. 6 times 2/3 is 4, and we add. 23 plus 4 is 27. We multiply. 27 times 2/3 is 18, and then we add. 0 plus 18 is 18. We multiply. 18 times 2/3 is 12. Negative 12 plus 12 is 0. Now we knew we were going to get a remainder 0, but here's our other factor. We've found that our original polynomial factors as x minus 2/3 times, well, the 6, the degree will be 2, so 6x squared plus 27, next term is an x, plus 18. Oh, but notice, look at these numbers. We have a 6, a 27, and an 18. Those numbers all have a common factor of 3. And that's not a coincidence, right? We really needed to have a multiple of 3 in each of these places. Otherwise, one of these guys would have been a fraction. And if that had happened, we would have ended up with a fraction forever. And we would certainly not have gotten a 0 for our remainder. So we needed each of those coefficients in the other factor to be a multiple of 3. Watch what happens when we factor out that 3. So our 6x squared plus 27x plus 18 is equal to 3 times 2x squared plus 9x plus 6. But then our original polynomial factors as x minus 2/3 times 3 times 2x squared plus 9x plus 6. We can reorder this so that the 3 is here instead. What good does that do us? Well, if we take the 3 times x minus 2/3 and distribute it, we get 3x minus 2. Our original polynomial could be factored as 3x minus 2 times this part here, 2x squared plus 9x plus 6. And notice, this has all integer coefficients. Instead of x minus 2/3, we have the factor 3x minus 2. And that's always going to happen as long as all the coefficients in our original polynomial are integers. And that's what this corollary here says. And so this is the factor theorem with integer coefficients. If we have a polynomial p over q in lowest terms, so that in lowest terms means 2/3, not say 4 over 6, right? The fraction is fully simplified. If we have a fraction p over q in lowest terms, and that's a root of a polynomial, then qx minus p, so that'll be the denominator, times x minus the numerator times p is a factor. And the other factor has integer coefficients as well. So we can factor it fully with only integer coefficients. And the factor that goes with that root we can write as qx minus p. Now I said this is a corollary. What does that word mean? A corollary is a theorem that's easy to get out of another theorem. This is a corollary of the factor theorem that we met before, the one that said x minus 2/3 was going to be a factor. Now corollaries in general have one of two kinds of proofs. They either have proofs that are really neat and interesting, or they have proofs that are really messy and boring. This one has a proof that is really messy and boring, so I'm not going to subject you to it. But this is going to be very useful to us when we're looking for what the roots of a polynomial might actually turn out to be.